G'day, this is my extreme entry for the 555 contest. It's an adding machine based on 102 555s using sequential logic based on the ability of the 555 to implement a SR flip-flop. Okay, let's turn it on. I'm running it here off a lantern cell. See, it has a reset feature that puts it into a zeroed state. The machine is essentially an accumulator with 9 decimal digits with carry chains between the digits and another register which is used to index the digits, and you can clock in using an old rotary telephone mechanism the numbers that you want to add. I've done it most significant to least significant digit first because that's generally the way humans input numbers, and it's capable of doing addition and subtraction using 9's complement arithmetic. Okay, before we do some math with it and talk more about how it actually works, let's have a look at the implementation. You can see there's rows and rows of 555s. There's some RTL logic as well that's used for the carry chains and for the clocking mechanism. There's a bunch of reset rails and clocking rails. The indexing register is basically a 9-step version of these decade counting cells. And there's a multiplexer as well, which is implemented using the pull-down transistors, the discharge transistors in the 555s of the indexing ring. There's also 3 debouncing circuits, mainly for the buttons. The dialing mechanism is excellent. It's surprising how bounce-free it is. The contacts in it are a beautiful piece of engineering. I used to take these apart when I was a kid, and I actually had to order this on eBay because I no longer had one in a working condition. It's really a wonder of mechanics. The mechanism produces very accurately timed 100 millisecond interval pulses, and it has 3 different contacts. One's for the actual decadic dialing that you get. For each impulse as the thing counts back to its rest position. And there's also 2 contacts that implement the start and end of the dialing sequence for each digit. I use them to advance the index counter so that I don't have to have a switch or anything to switch between decades. It automatically clocks around the decades. So there's also a manual clocking button on the front so that you can shift to where you want to start entering digits. Note here that there's also a switch that controls the carry output from the end of the decades back to the first decade. This is used to implement carry around. I've got it switched on by default, but you can switch it off if you don't want carry around to occur. Carry around is very important for 9's complement arithmetic for subtraction. You can see when I first fire it up, particularly on lower voltages, it doesn't always come up in a reset state. There is a reset circuit, but it only operates correctly on the design voltage. I'm running it here off 6 volts, not 9 volts, as it was originally designed to run off. But the reset system takes it back to a well-known state, with the 9th column being the first input column, and all of the decades set to 0. So I can dial in some digits. That was a 6. That was a 9. 5, 3, 6. Now if I want to skip a digit, I can either press the shift button and skip to the next column, which would be a 0, or one thing that I use that I cheat is I advance the wheel just a little bit and then let it go and it skips over to the next decade. This is kind of a function of the way the switching works inside this rotary dial. But it's quite a handy bug, I guess you could call it. That was a 4. Okay, and you can see once it gets to the end, it wraps back to the most significant digit ready for the next digit to be input. So we can dial in something else. Let's go 1, 2, 3, 4. Note how the carry works. 7, 8, and a 9. Alright, let's do some more controlled maths with it. Let's reset it back to 0 and let's dial in 1, 2, 3 and add to that 4, 5 and 6. The answer is 579, which is correct. Okay, let's do some subtraction now. Let's subtract 123 from 456. Reset the machine. Put in our bigger number, 4, 5, 6. And now we need to put in the 9's complement of 123. The 9's complement of 123 is 876. 8, 7, 6. You'll note that the answer here, there's a carry into the next column, and 332. The expected answer is 333. Now, with the carry around feature that this thing implements, if I'd clocked in the leading 9's for the 9's complement of 0, it would have carried right around and given me, the correct answer without any additional math. I can actually add 1 manually and ignore the carry out, or I can reset the machine and do it all over again properly the way it should have been done. Let's do that. Let's reset it. Oops. Clock in 4, 5 and 6, and now let's clock in 9, 9, 9, 9, 9, 9, 8, 7, 6. As you can see, the correct answer, 333. One thing we should talk about is subtraction where the answer is negative. Where the answer is going to be negative, there's no corresponding carry, and the result is in 9's complement. So you have to manually convert it back into the negative number. Essentially the 9's complement is the representation of the negative number. You can consider it as a sign bit. There's a number of different ways of thinking about it, but we can do the same kind of calculations again. Say we want to subtract 456 from 123. Let's do that. So we clock in 123 and we clock in the complement of 456, which is 543. See, the answer is 666, but there was no carry produced, so that means that is actually 666 in 9's complement, and the 9's complement of 6 is 3, so minus 333, which is correct. We'll talk a bit more about 9's complement arithmetic in a minute. Diagrammatically, this is essentially how the machine works. There's an accumulator, which is made up out of these decade rings. The decade rings are all chained together with their carry chains. Each individual decade has an increment line, and when a pulse is driven into the increment line, the counter hops to the next digit. These digits here, I've obviously represented them with 10 LEDs. I could have just as easily used a decoder to decode them to drive a 7-segment display, or perhaps some Nixies. I was actually thinking about using Nixies, but I decided not to because I figured they were a bit expensive, and I didn't have 9 of them to spare. I have a few less, and one day I'm going to build a clock out of them. The dialer produces 2 signals. It produces a next signal at the end of each digit that's dialed, and it produces a count signal. The count signal is a bunch of negative going pulses for each number. So if you dial 1, you get 1 pulse. If you dial 9, you get 9 pulses. Then you get a pulse on the next line. This is really convenient because it meant that it was quite simple to implement the multiplexer by using the indexing register, and you just step the indexing register at the end of each cycle, and eventually it steps right around and you're ready for the next number to be put in. The carry around is also mentioned here and shown as a switch, that it can be switched out. I was considering putting an additional cell right at the end to implement essentially the overflow indicator. If carry around was switched off, you'd switch the output carry of the accumulator into the overflow one shot, or you know, essentially it would get triggered if there was an overflow, and there'd be an additional LED saying, "Yep, you ran out of resolution in the accumulator, and your answer is too big." Essentially, with a you know, a normal calculator like this little $3 device here, you put something too big in, you get an E on the screen. Same thing. Here's some method of complement maths. Essentially, positive numbers represented 0 to 9, negative numbers represented by their 9's complement, which is 9 down to 0. The addition is just how we all do addition. The carry chains automatically take care of that, so 7 plus 5 is 12. 7 minus 5, however, means 7 plus, it's the 9's complement of 5, which is 4. We add them together, we get 11. The carried out digit is then carried around and added back to the LSD, and the result is 2, which is correct. If the number that you're subtracting from is smaller than the number you're subtracting, then the result will not have a carry. So here, 9's complement of 7 is 2. Add them together, you get 7, but no carry. So this 7 is represented as a 9's complement. The 9's complement of 7 is 2, negative 2, which again is correct. 5 minus 7 is minus 2. This works for 0. The 1 minus 1 is 0, which is 1 plus 9's complement of 1, which is 8. This gives you 9. 9 no carry means 9's complement 0. Works for multi-figure digits as well. As long as you clock in the leading 9's, the automatic carry out gets added to the least significant digit, and you get the right answer. This is a very old technique. It's been used for years. Many of the earliest computers were actually decimal computers. They were not digital computers. This actually works for any radix. You can have the radix complement and the diminished radix complement of any base that you build your machine, or you use your numeric system, and it will all come out correct for addition and subtraction. Okay, so we've talked a bit about the maths, and you've seen the device working. How does it actually work? How do we use 555s to implement sequential logic? Fortunately, every 555 is essentially an SR flip-flop with 2 Q outputs, one of which is open collector, and the other one has a totem pole output, so it can sync all source current, which is useful. It also has an additional positively asserted reset line, which I found quite useful for the reset of the entire machine. The set and reset lines, though, are negatively asserted logic. You can see the little inversion bubbles here. So they're driven by negative pulses. This actually turned out to be quite easy to implement. You just have some pull-up resistors, and you drive the pin low for a minute. The device sets or resets as you want it to be driven. In order to make things less confusing, especially with metastability, or the problem is if you drive both S and R together in a normal flip-flop, the thing will oscillate like crazy, and you don't know what happens, what result it will be when you remove the drive. We can use edge-triggered logic. Edge-triggered logic is very simple to implement with the 555. You just use capacitive coupling. You pull up the particular negatively asserted pin you want, and you couple via a capacitor into it a negative going pulse. The capacitor will then recharge back through the pull-up, and it will give you, an impulse waveform that will trigger the device, and then you can leave the thing pulled down on the other side of the capacitor, or you can release it and the positive going pulse will not trigger the device. This is really handy. It's essentially how each of these chains is implemented. The output, the Q output, the totem pole output, is capacitively coupled into the set of the next stage, the next 555. So that if it was positive, there'll be a negative going edge when I pulse the reset line. So the clock for each digit in the ring is actually implemented by resetting all of the 555s together. Any of them that were in the asserted state, positively asserted output state for Q, will then generate a negative going edge as they reset, and that reset will get propagated into the set of the next 555. Fortunately, the 555 reset voltage is actually less than the set voltage, so if you apply negatively asserted set and reset at the same time to a 555, it'll come out of reset and set before it recovers completely, because the reset voltage is lower than the set voltage. And this is a really handy feature, although my device doesn't actually use it. It's more of a timing constraint because of the way that the RC constants work. but it's particularly useful or particularly annoying depending on your application that the device comes out of reset at a different voltage than it actually sets at. Okay, so using all of that, this is what the decade rings look like. We've essentially built a D flip-flop out of an SR flip-flop, an edge-triggered D flip-flop. So I've got an edge-triggered clock, which is applied to the reset pins of all the 555s at once, and we arrange for the total machine reset line to actually set the first or the 0th D flip-flop at during reset. So as it comes back out of reset, it pulls down the set input on the first one and it gets asserted. The decade ring itself is a bit like a bucket brigade. You can actually use it as a delay line memory. If you whatever pattern is in this cell, whether it's 1 or 0, gets propagated to the next cell after reset. So you can clock through the pattern. I'm only using a one hot pattern where one particular cell is asserted at one time and then it gets clocked around the ring. Obviously, if the reset didn't work properly and the thing came up in some bizarre state, you're going to be clocking that pattern around the ring, and that's useless. Or if they are all 0, that would also be useless. So it's very important that the reset mechanism sets all of them, basically pulls them all down long enough for the pull-ups to recharge, and then asserts the first cell when it comes back up. The multiplexer that I use to decide which particular digit is going to get the clocking pulses from the dialing mechanism was actually worrying me for a while, but it turned out to be quite simple to implement. The pull-down discharge transistor, the open collector transistor, pin 7 on the 555, is very useful for this. We can just use a bunch of resistors to distribute a positive going pulse for the clock line, which is easy to implement with some RTL inverters, to every decade's clocking line. I use positively asserted logic on the clocking lines, and then it gets flipped over with a pull-down RTL. I'll post the circuit diagrams later. They're essentially the same circuit over and over and over again, but it's pretty straightforward stuff. So the clock pulse for the increment for each digit is applied through a bunch of resistors, and the pull-downs for all of the Q lines, pin 7s on the 555, stop the pulse from getting propagated to the particular digit that we don't care about. So while there's only one hot in the index register, that particular one, when it's asserted high, means that, because the transistor is driven by the complement of that particular impulse will not be pulled down, not be rejected, so it'll go through and it'll clock the individual digit. You can see it's implemented like this. Increment comes in, gets split up into a bunch of resistors and goes through into each ring, and whichever 555 is currently active out, active high, will get allow the signal to pass through. As you can see, this turned out to be a pretty complicated machine. 102 555s to implement 9 decimal digit adding machine. I had plans to build something a little bit more complicated, but in the available time that clearly wasn't possible. I wanted to build something more like this, which had multiple registers. The accumulator and the indexer are part of the machine that I wanted to build. I wanted to build something with 2 additional registers. The dialer mechanism would have been the same. I was actually thinking about implementing the dialer mechanism using 555s to automatically do the complement, so that you don't have to do the complement by labeling the dialer with negative digits, or by doing it in your head, doing the complementation in your head, and having an operation where you can have, say, the 4 functions of a calculator, maybe even square root, depending on how complicated you made the control logic. But the control logic is the hard part. These 3 modules here that I've labelled are very non-trivial. Although the X and Y registers will be almost as complicated as the accumulator, they don't necessarily need as many digits. They're obviously time-consuming. They would take up hundreds of 555s in themselves. The control logic would be quite a undertaking to implement. But essentially it becomes a micro-coded CPU. You could use a diode ROM to implement the control store, and the control logic would be a whole bunch of 555s and some RTL logic to set and listen to various signals coming back from other parts of the machine. I thought quite a lot about this, and I have some reasonable designs that I think I could implement, but it would take hundreds and hundreds of 555s and many more hours than I had to implement. For example, here's a sequencer that's can be built with 555s. You can use an array of monostable and bistable 555s to implement a triggered sequencing system. You can trigger it, the monostable goes high for a little while, then eventually it times out, goes low. That negative going pulse can trigger the next monostable. This is like the traffic lights video that I posted about a week ago now. And partway through this sequence you can have a bistable that gets triggered. It then waits until some kind of continue signal from elsewhere in the machine comes in and resets it, and essentially the chain goes on. This can either be looped, or the whole thing can be a big asynchronous systolic array kind of logic machine. The thing that I had in mind was to use a sequencer like this to index a diode ROM. The diode ROM would take feedback signals from elsewhere in the machine and produce new control signals that went out to other parts of the machine. You can obviously use indexing of different places. You can tap off these rings to do complementation, and you can have, clock a certain number of events until something happens, that kind of thing. It can be controlled by the diode logic. This is a truth table for a 7-segment decoder that can be built with diodes. It's essentially also a diode ROM with 10 lines in and 7 lines out, and driving Nixies for the display would be just a matter of high voltage pull downs, high voltage transistors driven by the one hot outputs of the rings. So it's certainly doable, but it's a heck of a lot of work if you want to build a more non-trivial adding machine. Here's some historic context for my machine. This is the Pascaline. It was made by Pascal in 1642. He built a few of them. They were never really mass produced. Technology of the day was a bit limited, but he solved many of the problems associated with carry chains. In particular, he built a mechanism that stored energy for each rotation of the dial. As you dialed each of these digits, partway through they started to store up energy, and then they would use the energy at the end where the carry had to occur to push the next wheel one step. I think he called it the sorter mechanism. And previously, basic mechanical wheel machines where you've got a wheel that's going around and there's a cam on it that knocks the next one on, when you get 999 and you have to perform a carry across multiple digits, the mechanical losses associated with that make it quite difficult to carry beyond 3 or 4 digits. When I was a kid, I used to have one of the, sort of a 3-digit version of this. It was a red plastic carry machine. It was labelled in cents, dimes and dollars, obviously for the US market. And you would go around the shop while you were buying things and press the buttons on the top. It had a button for each decade, and it would it'd add up your order, and you could check when you came to the cash register and make sure that your calculations compared with whatever the checkout person was doing. It's obviously a fairly limited machine as far as multiplication and division goes, and certainly square roots would be very annoying to do on this machine. The only way to do multiplication and division is to do repeated addition or subtraction. It does 9's complement arithmetic the same as my device does, although my device is slightly more ergonomic in that it has this indexing register so that you don't have to individually go to each digit and dial it. It was dialed much the same as mine, like a telephone. You put a stylus in each of these little digits and you pulled them around to the stop. Reset on this machine was obviously also a pain. You had to, there's a specially labelled digit here that's essentially where it says 0, and you dial them around until you've zeroed out the register. It's basically a manually operated accumulator, a very simple adding machine. Kind of the same level of ability as my device, so this one obviously only has 6 digits. I don't know how many they were built up to. It took quite a few years after that before the first truly, I suppose, 4-function calculators were made. This is a picture drawing of the stepped reckoner. This is something that Leibniz came up with. This is really the first true 4-function calculator. Although multiplication and division and square roots are done using an algorithm that the user has to input, it has 2 additional registers, and those registers really make a huge difference. This is the same accumulation register, but it has an input register. Basically whatever you want to multiply by or add repeatedly gets input, or subtracted repeatedly if you're doing division, gets input on these dials, and then you turn a wheel and this gets added or subtracted from the accumulator. There's also an additional register here that counts the amount of operations that you've performed. This screw acts as a barrel shifter and shifts the carriage up and down so that you can do multiplications far more efficiently. Say you want to multiply by 98, instead of multiplying by rotating this crank 98 times, you go to the next, go to the 100th column, you do one addition, which is the same as multiplying by 100, and then you go back to the units column and you subtract twice, and that gives you multiplication by 98. This register would then say 98, and your result from your multiplication would appear in the accumulator. This basic architecture is what all following machines used right up really until the 70s, until we had digital logic that was cheap enough to implement. All mechanical and electromechanical calculators work pretty much the same way, with 3 registers, carry chains for the accumulator, and some kind of counter that counts the amount of events that you've done. Later machines were button based rather than turn the crank kind of based, but essentially Leibniz was the guy that really nailed the problem of mechanical computation. In the 1670s, obviously manufacturing technology was fairly limited, and building the machines back then was quite a challenge. It wasn't until Thomas de Comma in the 1850s made the machines practical to be mass produced. Same kind of architecture, barrel shifter, input register, operations counting register and accumulator. He had decimal point markers for doing floating point arithmetic. It's essentially the same architecture. His very first machine that was designed in the 1820s actually did single digit multiplication in hardware. You would pull a string or crank a wheel and it would do a multiply algorithm for you, but only for one digit. Later machines, to make it affordable essentially to produce, he had to remove that feature, and it became essentially the same as Leibniz's machine, but in a way that was far more practical to produce using the technology of the day. The company that he started went on for many years and produced mechanical calculators right up into the 1900s and beyond. Essentially he created the industry of mechanical calculations. It wasn't really until the post-war period, when the Curta came along, that true small mechanical calculators were available. The Curta is it's a very cute little device. This is actually a little bit bigger than life size. It's handheld style device. This is the input register. This is the accumulator, and this is the instruction counter, and this is, I guess you could call, the clock. You turn the handle, it looks like a pepper grinder, doesn't it? You turn the handle and it adds whatever's on the input register to the accumulator, and if you want to do subtraction, you pull the lever up before you rotate it, and it automatically does 9's complement arithmetic for you. Inside there's a wheel with a bunch of cams on it, and there's 2 different rows of cams for each digit. The one row is positive, and the other row is the complement that's done for subtraction. It handles the carry around or the carry overflow for you automatically. It's got movable decimal place pointers, and the clearing ring here, which is shown folded in, you cycle that around to zero out the device, and that's your reset. It's quite a story, the Curta. The chap that came up with it, he was imprisoned in a camp by the Germans, and was essentially he would have been dead if he hadn't have come up with this idea and was encouraged to build it. It wasn't until the post-war period, when he was liberated, that he actually got access to the facilities to build it, and there was hundreds of thousands of these things manufactured. They're quite expensive now. I think the cheapest I've ever seen them go for is about $600 Australian, up to $1,000. They're quite a collector's item. There was multiple versions made. There's a large version with more significant digits, but essentially they're still a Leibniz style accumulating multi-register machine. They're sort of a cross between a pinwheel machine and the early arithmometer style machines, but they're very small and obviously post-war manufacturing technology was the key in being able to build something this small and this really cute of a device. It has a barrel shifter too. You can rotate the barrel, and that gives you your algorithmic ways to multiply and subtract and divide by large numbers. And square root is, well, it's a bit of a grind to grind out the result, but the algorithm is there for multiple divisions, and it does work. So in historical context, I guess my machine is most similar to the Pascaline. It's quite a simple accumulator, essentially, with an indexing register to make it a bit more expedient to use. It's doing additions and subtractions is easy, multiplications and divisions is obviously a lot of work, and the full machine that I wanted to build would have been able to do the 4 functions, but yeah, building it using 1970s level technology of 555s and RTL logic would take a considerable amount of time. It's probably quite practical to build something more like a Curta using the technology that, say, 74 series logic. It should be possible to use 74HC logic, or perhaps the 4017 if you want. 4017 kind of gives you everything that you need at once. So these decimal registers, decimal rings in my device are essentially an implementation of a 4017 using 555s and a bit of RTL. So it wouldn't be too difficult to build something more Curta-like, maybe even in a circularly symmetric geometry using 4000 series or 74 series logic. Alright, that's it. Thank you very much for listening. I've had quite a lot of fun with this 555 contest. I still haven't got an entry for the minimal category. It's probably the most challenging category to kind of come up with something brand new, but also trivial, using a chip that's been around for so long and so many people have built so many wonderful things with over the years. I'll be writing up the more detailed circuit diagrams on my website soon, probably the next day or two. And I'll obviously add a link in the video description for that. And I can't wait to see all the other entries. I know there's some very stiff competition. There's some fantastic projects out there. I particularly like the 555 video game that I saw last night. It's quite extraordinary. One of my designs was for Pong, but again I thought Pong was far too complicated to get working, but not sure enough that bloke nailed video generating project with collision detection and audio in only about 20 odd 555s I think it is, and some op amps and a bit of logic. Very impressive, and can't wait to see the other entries. I'm sure there'll be some equally amazing stuff that we haven't seen yet. Alrighty, thank you very much.